Well, greetings, Mr. Kolazar's class. Today we're going to move from ionic bonding to metallic bonding. Now, metallic bonding, we're going to be looking at, instead of our give and take of electrons, our idea today is we're going to be looking at what we know as the C model, or the sea of electrons, and then we're also going to look at a different type of metals with our alloys and the properties that they can have. So, to begin with, metallic bonding occurs between an M and an M. That's short, remember, for metals. So either two of the same metal or one metal and another type of metal are what we're going to have when it comes to metallic bonding. And how we're going to look at metallic bonding, instead of giving and taking electrons, we're going to look at what's called the electron sea. So the electron sea model is going to be our valence electrons for metals form a sea of electrons which surrounds the metal cation. So remember, the cations, cats are positive. So our nucleus is the positive portion of the atom, positive portion of the atom, positive portion of each atom. So what I'd like you to do on your page is kind of just to draw out some of our positive atoms. Now this is not only the nucleus, but is all of the inner electrons also. The valence electrons, or the outer electrons, instead of being around the atom, are kind of just going to be floating around in between that positive central part. The nucleus and those inner electrons give a positive overall, and the negative outer valence electrons are free to kind of move from one atom and float around to another and kind of just continually are moving around. We're going to call that our sea of electrons. Those valence or outer electrons are not stuck to just one atom. They kind of are moving around between each, and that's what gives the unique physical properties of metallic atoms, or metallic bonding. So these electrons are said to be delocalized. So delocalized, the sea of electrons, those outer, the valence electrons for metallic bonding, are said to be able to be free to move. So delocalized, meaning they're not stuck in one place. Allowed to transfer heat and electricity due to this. Now our delocalized electrons, kind of that same sea of electron model, if we were to think about an element, we'll go with potassium. Potassium, if you were to look at its electron configuration, argon, 4s1. Now that outer electron, that s electron, is allowed to move away, and we're left with argon would be what the electron configuration is, or potassium with a +1 is what it actually is. So the rest of the potassium atom would be our plus part, and that outer delocalized electron, that one in the outer energy level, would be the negative part throughout. And then the positive parts of potassium would be each of the nucleuses and all of the inner electrons there. So that outer valence electron is the delocalized one. It's allowed to freely move around the rest of the atoms. It's not stuck with just one like the ionic bond is. So that gives us some of our properties of metallic bonds. They're allowed to be malleable. If you can hammer it into thin sheets or into other materials without it shattering. Ductile, to mean it can be drawn into a wire. Durability, if it's struck or hit, it can retain its shape. So last, with our ionic bonds, we hit, and eventually the positive and negatives moved over and the positive lined up, allowing it to shatter. Now with metallic bonding, if we were to strike an object with a hammer, instead of it shattering, it'll bend or tear maybe, but as it hits, it'll move those positives over, but the sea of electrons, all of the sea between, as the atoms move, they are still connected with that sea of electrons, and it's allowed to bend or deform the material without it changing its shape. And a lot of times it'll bend right back into its original structure. If it's allowed to, it'll take some of that force and then bounce back. It's that sea of electrons that allows these properties to happen. So that's what's holding our metals together. So anytime we think about our regular metals, like a paper clip, you can bend a paper clip back and forth and back and forth. It's from that sea of electrons. Metals are conductive. of heat and electricity because those delocalized electrons are allowed to transfer that heat and electricity. So we've got our hot oven from metals conducting electricity, electricity flowing through power lines. Those are materials or metals are conductive of electricity. Those electrons easily move, causing that heat and electricity to be easily transferred. Metal's hardness and strength can vary from those d orbitals depending on which element we have. Since they vary, we're not going to test on this, so you don't need to worry about that part in the notes. And our last part, alloys. Homogeneous mixtures, so evenly mixed mixtures composed of an element, metal, and another metal or another element. So the nice part about these is the metals chosen depend on their desired properties for the consumer or manufacturer. So as we're going, it's an even mixture of different metals are evenly mixed throughout. Our solution is what we're going to know them as also. So some of these ideas, why we need them: iron, 98%, and carbon 2% give us steel, one of our biggest building blocks for all of our structures, materials, infrastructure of society. Other ones, stainless steel, iron, chromium, and nickel give us our silverware. Wouldn't want our silverware rusting because that would make our food taste gross and maybe be a little painful. So as we're going, that allows us to have a material or an alloy that's very useful there. White gold or yellow gold is going to be a little bit different. It allows, zinc and silver and copper along with the gold to give it a little bit of hardness and strength. White gold is got some platinum or palladium in it to give it a little bit more whitening and durability. Brass from our instruments. Brass over here is going to be copper and zinc to give us that durability and hardness, plus the nice color that you see. So all those alloys helping us out, mixtures of different metals. And then just to end with another casualty of the war of the sodium atoms. We've got two sodium atoms, one saying to the other, I'm hit, I've lost an electron. Second one looks back and goes, are you sure? And the first one says, I'm positive. Ha. Losing an electron, become positive overall.